Well, hello. I've been working on a DSP today because I wanted to change up my day because I've been nonstop working on a sound generation. And to take my mind off sound generation, I actually turned to sound processing. Matter of fact, been looking at DSP, which is a digital signal processor. And in very simple terms, when you have a data, you want to change the data a little bit, and then you want to change it a little bit more, and you can segment this into a pipeline. So if the data were to be sound, you want to kind of pitch it up, but then you want to equalize it, and that means you're transforming the data, as they call it. And transforming just means changing. The way most digital audio workstations do it is they build a digital signal processor graph. And this graph is a representation of how the data comes in. Then it goes into a particular processor, and then that is connected to another processor, and that is connected to some output, usually your speaker, and the sound editors. And these processors can just be seen as plugins. So really, we're talking about VST plugins as a processor, your generator or synthesizer as like the data coming in, and then the output being your speaker. Now, I made a very basic setup. What I've done is made something called a sync, a generator, a processor, a generator-processor connection, generator-sync connection, etc., etc., etc. This is very verbose code that I wrote. Very verbose. Verbose in the sense that I really try to model simply what I would imagine like FL Studio to kind of be like. And not FL Studio in particular, but I like saying FL Studio. I just mean audio editor. And what you have is a generator, which is something that makes sound. It could be because it loads in a sample, or it could be because it's a synthesizer. You have a processor, which really it takes data in and puts data out, as opposed to the generator, which just outputs data. And then the sync is just a module or a node that takes data in but doesn't put anything out. And that could be for logging or whatever. It's very abstract. Anyway, so then you have the whole process generator. It finds all of the connections between them. Now you can only have 4 different connections in the setup between the generator, the processor, the generator, and the sync, the processor and another processor, and the processor and a sync. This is going to all sound very confusing, but that is to say that if you want to create a pipeline where you have a function and that function can take in data, it can also be connected to another function. And this way you can change the output entirely. So it can go through a pitch adjuster, and then through an equalizer, and then through an X, and to a Y, and to a Z. What is the problem with this graph setup? The problem with this graph setup is on many levels. First of all, I wrote it. Always problematic when I write it. Secondly, it is in a managed language. We're using C# here. So C# managed language. These days, there's a lot of workarounds to make it faster and to have better memory and garbage collection and blah, 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 and all these words and buzzwords. And so if you're making something that requires a lot of operations to happen very quickly, you're better off using a lower level language like C++ or Rust. Especially because a DSP, a digital signal processor, can also be dynamic, which is what mine is. Dynamic means we have a block of data coming in, and a block is just a chunk, so a little bit of our larger set, and we want to quickly put the data, transform it, and put it back out. Well, I said quickly. So that means that there's a time limit. And if there's a time limit, what you know is that you don't use higher level languages to do it. Unless you do interoperation. So if I were to build out this fast signal processing in C++ but call it in C#, that's still feasible, but ultimately you want to do that in a lower level language. The third issue, I don't know what I've been yapping about, but C# is very slow. You don't want to have it in this particular setup because you have dynamic generation. And I've tried it. I got very bad results on my first go around. Now there's things I can do better, like where I make the data, I could share the data, but you can see that basically you're trying to squeeze performance out of a particular way of working. So no matter what I do, at the end of the day, there are fixed problems with a graph that you just cannot solve. You cannot optimize further than a specific bar. But what you can do is think of the problem differently. So as I was making this, I thought to myself, this seems so familiar. And it seems familiar because if you've ever made video games, this looks a lot like entity component system. Like an entity component system solution could work great here. And what is an entity component system? Well, an entity component system is, instead of having everything turn into objects with their own inheritance and their own little connections and the processor hopping from one memory to the next, we lay everything out contiguously. I can't say that word. Contiguously. And when you do that, you basically put all of the memory of some data in one part of the CPU and then other data in another side. And when you're accessing it, you're accessing all the memory at once and it's not scattered. This prevents cache misses, and it also separates things from a framework perspective because you are basically separating the data from the actual functions. And I've done that here. Now, that sounds very complicated, but I'm going to be honest with you, it's actually much simpler if you are not familiar with object-oriented programming, but you want to explain programming to somebody. The entity component system is much easier to understand because it's more data and functional oriented. So what you do, instead of having a oscillator generator or a synthesizer, I separate it. I have this data concept called synthesizer parameters or oscillator component, and then I have this system called oscillator system, which takes in all of the components and it applies these same functions all at once. So instead of having 4 oscillators with the data inside of it, I have 4 oscillator components, which is just data, and 1 oscillator system. And your computer is going to be much happier doing this. And when it comes to digital signal processing, it works just amazing. It solves exactly the issues that you're having and you're desperately trying to solve when you're working, for instance, with C# in a graph. Now, what you do lose is flexibility because there's one thing you can't really do with this, which is dynamic mapping. I can't tell it to first do one thing, then go through another pipeline, then go through another pipeline, then go through another pipeline. The only way you can do that is by having all of these go through the pipeline at once, but basically just disabling the parameters. So all of them get equalization, but only one of them actually has equalization to any of the frequencies. The rest is just set to 0, for instance. Now, there is a hybrid version, I think, which could be possible, which is if you start to consider that really all of this is just basically a function that takes data in and has a set of parameters and puts data out, and you could make these functions very, I don't know what the word for it is, but you can isolate the function itself. You can take all of the operations you want to apply to the digital signal. You can write the code dynamically. That is to say that we're going to have the program write the necessary code for this particular set of functions. And then only thing we have to do is pass the parameters. And I don't know if that's called just in time. I don't know if you call that compiling a kernel, but you are definitely compiling some code, and you do that based on the components that you are applying here. It's a completely different way of viewing the issue after signal graphing and the ECS, but it's a bit of a mixture of the two. Because what you're solving is all of these hopping around in memory and a CPU, but also you're separating everything into data and functions. So you have the flexibility of building a graph or at least a pipeline, but you don't have any of the issues that you would have with that. And so you have all of the benefit of ECS, of performance, but you don't have the negative effects of not having the flexibility. I hope I explained myself well. I have not yet taken a look into how to do this. I've seen some examples of it. Let me scroll up here. So you can do like an expression tree code generation apparently using C#. And what that basically is it's literally you're writing like you're basically writing code to write the code. And if each synthesizer or process can be considered this tiny transformation function, it's actually very easy to add new versions and new concepts to the pipeline. The only challenge then is, when do you compile the code if you're dynamically doing signal processing? When do you recompile it?